In the next few sections, I will talk about isomerism in transition metal complexes. There are different types of isomerism. First, linkage isomerism. Over here you have a nitrito ligand bonded to copper, but the bond can be formed between cobalt and nitrogen, or between cobalt and oxygen. So we need to specify dash kappa N versus dash kappa O. Dash kappa N means the bond is between nitrogen and the transition metal center. Dash kappa O means the bond is between one of the two oxygen atoms and the transition metal center. Second, ionization isomerism. You have to look at the counter ions. For example, over here, you have two bromine minus ions, two bromides that balance the overall charges. But over here, you have two chlorides that balance the overall charges. So what's going on here? Well, it is possible for these two chlorido ligands to form two bonds with this platinum transition metal center. And these two bromides are outer sphere ions. Now in this case, the two chlorides are outer sphere counter ions, while these two bromido ligands are directly bonded to the transition metal center. Now we have hydrate isomerism. So what does that mean? If I give you this formula, chromium trichloride hexahydrate, well, you don't really know what are the ligands bonded to this chromium transition metal center. So it can be this. We have 5 aqua ligands and 1 chlorido ligand bonded to chromium, or you can have 6 aqua ligands bonded to chromium. So over here you have penta, aqua, chlorido, chromium, and then you have this chloride here, and this is monohydrate. And then over here you have hexa, aqua, chromium, chloride. There's also coordination isomerism. So if you look at this formula versus this formula, they look almost exactly same. But over here you have 6 amine ligands bonded to cobalt. Over here you have 6 amine ligands bonded to chromium. Over here you have 6 cyanido ligands bonded to chromium, and over here you have 6 cyanido ligands bonded to cobalt. So this is the so-called coordination isomerism. And then geometric isomerism, you can do various permutations of ligand arrangement in 2-dimensional or 3-dimensional space. So we'll first talk about this geometric isomerism. Section 7.7, square planar complexes, will focus on geometric isomerism. So we're going to permutate the ligand arrangements. Now if you look at this transition metal complex structure, the transition metal M is bonded to A's and 2 B's. But now you can have cis. There's 2 A's on one side, there's 2 B's on one side, so this is cis conformation. You can also have trans conformation. You can have this 2 A ligands sitting on the 2 opposite sides, and the 2 B's also on the 2 opposite sides. So cis versus trans. In here you have 3 types of ligands. You have 2 A's, 1 B, and 1 C. In this case, you look at the positions of the 2 A ligands. Over here, these 2 are on one side, B and C on the other side. Over here, the 2 A's are on the opposite sides. And then we also name this cis, we name this trans. Now there's a linkage between A and B. So if this is a, let's say, bidentate ligand, it can have 2 points of attachments. So AB and then AB. So you have only 2 bidentate ligands here. And then if there's 2 A points of attachment are on one side, there's 2 B points of attachment are on the other side, it's cis. If A and B are on the opposite sides, we say this is trans. And also you can have 4 different ligands, A, B, C, D. In that case, you can have 3 different geometric isomers. The reason is you can have this AB on the opposite sides. And then, of course, CD will be on the opposite sides, and then you can have AC on the opposite sides or AD on the opposite sides. So those will give you 3 geometric isomers. Because I'm assuming this, in this case, A, B, C, D are in the transition metal are on the same plane. With a symmetry plane, this structure is achiral without any chiral center.